Good. Okay. Well, welcome everyone. Thanks to Greg for inviting me to give this talk. I think this will be fun. I want to talk today, possibly a first session. If there's interest, I can continue doing more of this, but just really a conceptual sort of introduction to the field of gauge theory in physics and also in mathematics. So the first part will be a prologue, and I should say, feel free to interrupt me. I hope this will be more of a discussion. So feel free to unmute and ask questions at any time or make comments or death threats or anything like that. But for now, we'll start with some motivation. So why is gauge theory interesting? So your time is valuable. So if I'm going to ask you to listen to me for an hour, I should attempt to justify why the stuff that I'm telling you is worthwhile or interesting. So I should convince you that it's worth caring about. And to do that, I want to start with three very brief examples, or vignettes, as I'm going to call them. One from kind of traditional physics, one from more mathematics, and one from the field that I work in, which I'm referring to as high energy theory. You could refer to that as theoretical physics if you like. And each of these vignettes is supposed to illustrate a piece of what gauge theory is, without really giving you the whole picture, but just to whet your appetite, if you like. So the first vignette is an experiment, a famous experiment in physics called the Aronoff-Bohm effect. And here's what it is. So if you fire electrons at a screen, here's a picture, but maybe it's useful to imagine a sort of cross-section. So here's just a cross-section of what we're doing. You fire electrons are coming in from one side. On the other side, you have some screen. So here's some screen. And in ordinary quantum mechanics, without any additional bells or whistles, you may know from the two-slit experiment that if you fire electrons at a screen, you get some patterns of dark spots and light spots. So here's an interesting fact. If you do this experiment, but now you put in the middle of this path a little solenoid, so it doesn't matter if you know what a solenoid is. We're really just wrapping a wire around some chunk of iron and passing a current through it, so it creates a magnetic field. So there's a magnetic field in the center of this experiment. And importantly, it doesn't really matter if the electrons ever get close to the magnetic field. So I can even shield this. I can put in a big chunk of some other metal like lead or something, which I'm drawing here with this dash line. So I can put in a big chunk of lead to shield the magnetic field. So this is guaranteeing that the electrons only travel through a region with zero magnetic field. So there's zero magnetic field out here. Despite that, even though the electrons never see a magnetic field, you still observe a measurable shift in the pattern on this screen when you turn on the magnetic field inside this shielded region. So this is surprising. This is usually the first experiment to motivate gauge theory in an undergraduate quantum mechanics course, that even with this shielding, the electrons have a measurable physical effect from turning on a magnetic field. Now, if Greg were giving this talk, he would say, okay, well, the reason why this is happening is that really you can, deformation retract this space into basically R2 minus a point, and now this space has non-trivial pi 1 because there's some winding around it that the electrons can wind around this point that's removed. But I don't want to use that language yet. I just want to kind of present the vignette for a little piece of intuition. Here's a second reason why gauge theory might be important. So you may have heard of the Yang-Mills existence and mass gap problem. So one of the millennium problems is demonstrating that one important gauge theory called Yang-Mills, which is somehow the canonical or most interesting gauge theory, the usual one people care about. And an example of Yang-Mills is the standard model of particle physics, which is extremely numerically accurate. But at the quantum level, we don't really have a good definition for Yang-Mills. And really, this boils down to the fact that the path integral has a measure which no mathematician believes exists, right? When we do quantum field theory, we write down integrals over some measure, and the measure we can't define. But nonetheless, if you just pretend it exists and manipulate it, you get extremely accurate results. So if you think that millennium problems are interesting and worthwhile, then by this metric, gauge theory and Yang-Mills are at least as important as the Riemann hypothesis, although that might be a somewhat controversial statement. And a third piece of motivation from my field is a different gauge theory called Chern-Simons, which is related to Yang-Mills, but it's somehow topological. It doesn't care about a metric or how we measure distances. So Witten famously showed in a 1989 paper that this Chern-Simons theory has certain observables called Wilson lines that you can calculate. And if you calculate those over some path which closes, so over a knot in 3 dimensions, the Wilson line computes something called the Jones Polynomial. And it doesn't matter if you know what that is, it's just an assignment to each sort of knot, if you will, a certain polynomial and a variable t. really a Laurent series, if you will. But and these, I mean, the definition involves kind of defining this trivial knot to have a Jones polynomial of 1, and then defining some skein relations that you can use to recursively define it. But I won't get into that. I just want to mention this to show that there's some depth here, right? That gauge theory is somehow connecting to topology and knot theory, which is interesting in and of itself. So that's our motivation. But now that I've hopefully whet your appetite and got you interested in the subject, I'm going to immediately turn around and say I will not answer any of the questions I've just raised or go into detail about any of the interesting features I just described, because much of the richness of those two vignettes, the latter two that I just said, comes from quantum mechanics and non-abelian gauge theories. Today I'm going to totally sidestep that issue, so I apologize, but I'm only going to talk about classical and abelian gauge theory, and I'm going to do it using very little mathematical sophistication. Really, all I want to do is give you a flavor for the subject using intuition, analogies, and pictures to really kind of give you a sense of what the subject is about. So that's what I'm going to do, and here's the roadmap. So the first part of the talk we just finished, that was the prologue, what is gauge theory? Why gauge theory, I guess. So next I'm going to motivate gauge theory from a physical perspective, the phase of the electron. Then the majority of the talk will be developing a little intuition pump, an economic analogy, if you will, for what bundles are. And then I'll conclude with a little bit about electromagnetism and then some remaining puzzles that we could discuss in future sessions if you like. Okay, before I do that, any thoughts, comments, questions, anything like that before I start? Please unmute since I won't see if you type messages in the Discord.
None yet.
No? Okay, good. Very nice. All right. So let me motivate the physical problem that this is supposed to model. So this will be a high-level overview, bird's-eye picture of what field theory is. So the stage for our field theory is going to be spacetime, and for today I just want to think of spacetime as R4. So it's just a collection of tuples, 4-element tuples where you have a time, an x, a y, and a z. Right? So really we're thinking of a time axis that's going upwards, and at each time there's 3 space dimensions, and this is supposed to model the world that we live in, basically. So a point of spacetime, a point of this calligraphic M, is a particular point in space, x, y, z, at a particular time t. So this is what spacetime is. And in this talk, I'll often use Greek indices like mu. Mu is just an index that runs over the t, x, y, and z, right? So, for instance, v mu is a vector that has a time component, an x component, a y component, and a z component. So this mu index is just a spacetime index. Okay, so that's the stage. What is a field? So I'm not talking about rings with extra properties. In physics, a field is just a function. A field is a function that, just from space-time into some other target space. So you should just think of a picture where at each point in space-time, your field eats that point in space-time and spits out some value. It's just a function that eats points in space-time and returns something. So for concreteness, you can think of the outputs as real numbers or complex numbers, for instance. So a nice intuitive example is temperature, right? So at each point in space and each instant in time, you can imagine putting a little thermometer and it reads out some temperature, which is a real number. So this temperature field is just a real valued field on spacetime. Here's just like what it might look like on a flat surface at a fixed time. Okay, but in physics, it turns out that the electron, which is something we'd like to understand for physical reasons, is better modeled as a complex value field. So the model of the electron I want to use is just a function, psi, which takes in a point of spacetime and spits out a complex number. And you might ask, why does it need to be a complex number? And roughly, it's because the complex numbers have a nice involution. You can take the bar of a complex number, and that corresponds very nicely to the fact that the electron has an antiparticle. The antiparticle is the positron. So just imagine the electron as, again, a function that's spitting out a particular complex number, which is shown here just with some purple bump or something. It can be either above or below the axis, and this is just an example of a complex value field. So here's our electron. And now I want to motivate a symmetry that any theory of the electron should have. So any real physical experiment I perform that involves electrons will measure real numbers. So I can measure something like an energy or an angle or some scattering amplitude if you're more sophisticated, but they're all real numbers. So if my equations for physical observables are all real numbers, and they involve this complex value field psi, then the observables had better only involve real combinations. So for instance, if you take the product psi bar times psi, if you multiply a complex number by its conjugate, of course that's real, so that's fine. That's a term that could appear in an equation for a real value. Bad terms might be like the square or psi times the derivative of psi, because these things are not necessarily real numbers. So any good physical term has to have equal numbers of psis and psi bars, because that will make it real. But this immediately means that the theory has a symmetry. So this was the prerequisite I was talking about. The only thing you really need to understand this talk is knowing that multiplying a complex number by, some phase, if I have some number z, and I multiply z by, e to the I theta, all that's doing is rotating z by some angle theta, right? So here's this new number, which is e to the I theta times z, and all that's really done is rotated my complex number by some angle theta. That's all you really need to know. So here's the symmetry. If I decide I don't like the output of this function psi, I would prefer to replace it by a different output at each point, which is just this number e to the I theta times the old output psi. That's a replacement I could make. But if I make that replacement, all of the good terms will be unchanged. So for instance, this good term we were talking about before, if I replace psi by e to the I theta times psi, well, the conjugate here is just going to reverse the sign of this angle, because the bar of e to the I theta is e to the minus I theta. So I'm left with, this is a typo, that should be a psi, I'm left with e to the minus I theta, e to the I theta, psi bar psi, which is the same. So replacing the output by this rotated output does not change any of the good terms. And if you've studied physics, you know that every continuous symmetry comes with a conserved quantity, and here that conserved quantity is charge. So electric charge is conserved.
Wait, so hold on. So multiplying by e to the I theta makes bad terms good? Is that what?
No. So multiplying by e to the I theta leaves any given good term invariant. So if I perform this action, all of the good terms will be the same as they were before the action. The bad terms will not be the same.
So that's the symmetry.
That's the symmetry. Yeah, by symmetry, I mean acting with this leaves good terms invariant. That's right.
Okay.
Good.
And you can only do this before, or when can you do this? Because I understand that the phase is important when you're talking about like adding wave functions or something. But
That's
it's
right.
not relevant when you're talking about like taking measurements because you just take the magnitude. So when does this only apply to like a single electron field, or when can we do this exactly?
Yeah, good question. So 2 comments. One, this is a statement about classical fields and not about wave functions. But the second statement is, if this were in quantum mechanics where psi, I'm kind of abusing notation because psi here is not a wave function, but if I were in quantum mechanics and I was talking about a wave function psi, I would be free to multiply that wave function by any phase that I like. And as you said, when you take norm squares to compute probabilities, it would drop out. When I cannot do this in quantum mechanics is if I have, say, 2 particles, 2 electrons, one here and one here, and I multiply them by different phases. So if I multiply the left electron by e to the I theta 1 and the right electron by e to the I theta 2, then the total wave function will be a sum of 2 terms, which now will come with different factors, right? And then you can measure it. You can measure interference between angles, is the point.
Good. But you can multiply with the same factor then.
That's right. A global phase, even in quantum mechanics, is undetectable. That's right.
Okay.
Good. Very good. Other questions? As I gratuitously sip my coffee. Okay. That's an excellent question because that actually leads into what I want to do next. Because here you can globally rotate by some angle theta. But I'd like to make a locality argument that we should really think about rotating by different thetas at different points and see what happens. So in physics, one principle that we use is locality. So if I, shake my hand on Earth, then physics on Mars should not instantaneously know about it and change, right? So the behavior of the field psi, at least for short timescales, should only care about what's going on near psi. So if I do this rotation, which I just argued to Tetra a moment ago, that would not be a symmetry, where I rotate by different angles at different points, you might say, okay, well, that's not a symmetry, but what if they're really, really far apart, right? So if electron 1 over here is on Earth, and I multiply this by e to the I theta 1, and electron 2 is on Mars, or even in the Andromeda galaxy or something, I multiply by e to the I theta 2. By locality, you would think that this should still be a symmetry, because these These particles are so far separated that they shouldn't possibly know about the different phases at different points. So somehow, at least for far away particles, you should be able to do different phase rotations at different points. So you could ask, where does this break down? What happens if we try to push this and instead replace psi by e to the I theta of x psi? So we're rotating it by a different angle theta of x at every point, right? So this is kind of the most general thing you could do, where you rotate by different theta, theta 1, theta 2, theta 3 at every different point. So this is certainly not a symmetry of some of the good terms we had written before. So here's an example. Here's a good term we wrote before. It's good because it has the same number of psi bars and psis. And again, this d mu, just think of this as a derivative. This is, for instance, you can just think of that as ddx everywhere if it makes things look simpler. So this psi times the derivative of psi, if I replace it by a rotation which is different at every point, this is not invariant because the derivative can hit the function in the exponential. And then I get this additional term, this I times the derivative of theta, which is not leaving the term invariant, right? We get the old term plus extra junk. So the term is no longer invariant because junk has been introduced. So now there's really two things you could do at this point. You could say, okay, well, that was kind of a strange thing to even attempt to do. Let's just give up and say that's not a symmetry. You shouldn't be able to do this. But I find that a little unsatisfying because, again, by locality, in a particular limit, as you take the things very far apart, you should be able to do this. So if you take option 1, you have to kind of answer like, okay, why is it all right far away, but it somehow breaks down close together? There has to be some length scale, at which point it's okay to do this rotation, and less than that length scale, it's not okay. I find that a little unsatisfying. So option 2 is say, okay, let's change the theory. Let's modify the theory so that this local phase rotation, where we rotate by a different angle at every point, is in fact a symmetry. This procedure of changing the theory to make this a symmetry is called gauging the symmetry, or sometimes we say promoting it to a local symmetry. And in the next part, I want to pursue this option 2 and just see what happens. Good. So that's the end of the... Oh, sorry. Well, first one more slide in this act. How might we do that? So if we attempted to gauge the symmetry, let's just think physically about what we need to do. So we would need to attach a little local copy of the circle to each point x, and that circle is going to track how much the electron field psi has been rotated at that particular point. And then when we act with this symmetry, we want each local copy of the circle to rotate by its own independent angle, theta of x. But then to compare the field at different points, we would need a conversion factor, right? Because if I rotate by different angles at different points, I need to compare apples to apples, so I would need some converter that tells me how an angle at x1 is related to an angle at x2. And this structure is exactly what we need, or the structure that we need is exactly a fiber bundle. So as Greg spoke about in his last talk, a fiber bundle is essentially the structure where you attach a local copy of some space at every point in another space. And this conversion factor is called a connection on a bundle. But in order to keep the talk accessible and light, I'm going to avoid the definitions of these objects for now. And instead, I want to back off a little bit from the physics and just talk about an analogy that, although it seems a little silly, the analogy will turn out to give us quantitatively correct equations for U1 gauge theory. So that's what's coming next. But before that, that intuition pump, any questions or thoughts on this electron phase act of the talk?
So for a candidate for that conversion factor in this case, could you just sort of use the rotation? I mean, because you know how much, if you have 2 different points, you know how much each one has been rotated by, right? So it would be pretty simple then to, just convert between them, because you could just rotate by the difference between the angles, right?
That's right, yeah. So you're saying
Am I understanding this?
Yeah, there's a point here and a point here, and you're saying if I connect these points by a link, all I need to do is say, okay, if this guy was rotated by theta 1, this guy was rotated by theta 2, then this little connection on the link, which I'll call A, really just needs to know about the difference theta 1 minus theta 2 to compare them. That's the...
Yes.
That's right, yeah. So
Okay.
that's right. Good. Other thoughts? None. Okay. All right, well, if there are no thoughts, then let's develop this economic intuition pump. And as a side comment, kind of came up with this when an undergraduate was asking me to explain gauge theory in my second year of grad school, and I was very happy when I came up with this analogy. But then I found out that a lot of other people had already made this analogy in other papers. So I'll post the slides and you can look at the references. But on the upside, that means I could steal some pictures from other people who have discussed this. So there's nothing new in this section. It's all stolen from other sources. Okay, so let's do something totally different. Suppose we want to think about measuring wealth and prices. So say we're in Germany, for instance. So in Germany, you could think of prices as lying on a number line. So here they're all in like euro, different values of prices. And we're going to imagine those different prices lying on a number line that sits on top of Germany. So that number line I'm going to call money space. So there's just a number line sitting on top of a country. That's it. Okay? So there's a symmetry of this economic system in the same way as there was a symmetry of the electron system. Here's the symmetry. Suppose we change all of the prices in Germany uniformly and at the same time. So to be very concrete, let's say we get rid of the euro and go back to the Deutsche Mark. So at time 0, we get rid of all euros. Everyone must convert their euros to marks at the rate of 2 marks per euro, and all prices and wages now instantaneously change to marks. Now, it's pretty obvious that here nothing has changed. You would not say, oh, I'm very excited because I had 100 euro before and now I have 200 marks, so I'm twice as rich, right? You wouldn't say that because everything is also twice as expensive. So literally nothing has changed. There's no new economic opportunities. There's no change in wealth between people. It's a symmetry of the economy because we've just rescaled the currency. Okay, that's fine for one country. Now let's think about what happens when we introduce many countries. So I'm going to attach a different number line above, each different country. So you could think of a collection of money spaces all measured in local currencies. So I'm going to have a number line that's measuring prices in local currencies everywhere. And I'm going to call this a money bundle, if you like. It's a bundle of money spaces where the base space is the collection of all countries. So that's something you could do. Now, you could ask, all right, well, we still have a symmetry if we globally double all the prices, as in the Germany example, if you just rescale by 2. But you would intuitively think that in this system, you should also be able to locally shift currencies and still have a symmetry. So for instance, if you change prices in the UK, if they double, then nothing has really changed. It's not like you're going to make money by moving from Germany to the UK because the exchange rate, which is like this connection between the electron phases, if you like, the exchange rate would compensate, right? The exchange rate changes so that now it compensated the doubling of the prices. So we expect this to have a local symmetry, the same type that we were arguing for before. So that type of transformation I just described, where we rescale local currencies and also change the exchange rates, is called a gauge transformation. So any quantity which does not change when you make such a transformation will be said to be gauge invariant. So here I want to pause a little bit and give you a challenge to think about. I hope this isn't too infantilizing, but I think it's a little fun to think about this exercise. So one gauge invariant quantity is making money. So suppose I give you these explicit exchange rates. So you can change Deutsche marks for pounds, or marks for lira, or for francs. So we've gotten rid of the euro, and now everybody has their own country, or each country has their own currency, and these are the exchange rates. So a question for you, just think about it for a minute or so. If I hand you one Deutsche Mark, can you make some series of exchanges, some collection of trades, which ends up making money? So at the end of the day, you have more than one Deutsche Mark, so you have more than you started with.
Are you soliciting answers, or are we just thinking about this to ourselves?
I'm soliciting answers, so if you have one...
Okay, so you could go from a Deutsche Mark to 1 pound. You could go from the pound to 2 francs. You could go from the 2 francs to 20 lira. And then you could go from those back to 2 Deutsche Marks, and then you'd have twice what you had in the beginning.
Good, perfect, that's right. So if you didn't catch it, let me just show what Tetra just said. So here's the arbitrage opportunity. You start with the Deutsche Mark, you convert to pounds, so that's a 1-to-1 ratio, so now I have 1 pound. Then you go from pounds to francs, so that's a 1-to-2, so I have 2 francs now. Then from francs to lira, which was a 10-fold exchange rate, so now I have 20. And then I come back to Deutsche Marks, and now I have 2. So I've made money. This kind of loop has somehow been an arbitrage opportunity. In economics, we call this arbitrage if you can have a risk-free profit. So good, I've doubled my money by doing that exchange. But I also argue that that opportunity is gauge invariant, so I can still make money if someone rescaled their currencies. So I'll show this explicitly. Suppose Italy rescales its currency. So before it was the lira, and now it's going to rescale by a factor of 10, by which I mean that they changed to a new currency called lira tilde, and 1 lira tilde is worth 10 lira, right? So in terms of lira tilde, the old exchange rate was, say, a franc is 10 lira. So now a franc will be 10 lira, which is 1 lira tilde. And a Deutsche Mark will be, again, 1 lira tilde. That rescaling, if these exchange rates compensate appropriately, that gauge transformation does not affect the arbitrage opportunity. So if we do the same series of exchanges that Tetra said, if I start with 1 mark, go to a pound, go from a pound to 2 francs, go from 2 francs to 2 lira tilde, and then my 2 lira tilde back to 2 Deutsche Marks, I have still made money. So the ratio of the final money to the initial money after such an exchange is gauge invariant. Changing the currencies doesn't affect it. So that's good. This phenomenon, where if you have a collection of exchange rates, or more generally a connection on a bundle, which has the property that going in a closed loop can change the state, you come back different from how you started, then the bundle is said to have curvature, or the connection is said to have curvature. And you may have heard this word holonomy. So a holonomy is this action where you go around in a loop and come back. So you've had some translation, if you like, on your money space. The reason it's said to have curvature is because, well, if you've studied differential geometry, you might have seen something very similar where if I start at a particular point on the Earth and I'm carrying like a pole with like a little arrow on the end, and I walk in a closed path on the Earth, so I start at the equator, I go to the North Pole, all the while moving my little stick around and keeping it pointing in the same direction. So when I get to the North Pole, it's like this, then I come back down, again carrying my pole all along, keeping it in the same direction, and then I come back along this path. My pole will no longer be pointing in the same direction as it was when I started. It'll be an angle alpha rotated. So going in a closed loop and rotating a vector is very similar to going in a closed loop and making money, right? This is just a connection on what's called the tangent bundle, and this is a connection on a line bundle. And they both have curvature. Okay, good. So that's the end of the intuition of this act. So just to recap, what we did was I wanted to describe currencies in the following way. I attach a line to each country, just like the circle in the electron case. We introduced exchange rates that will compare currencies between the countries, which is like this mythical conversion factor that I described but didn't define for you. And we also allow each country to independently rescale their currency. So if they do so, the exchange rates have to adjust. And this local rescaling of currencies is just like this local phase rotation of the electron that we want. And again, mathematically, the structure is a line bundle with connection. All right, so I said a lot of words. Next, it's going to be a little denser because I want to get some equations out of this thing. But before going to the one dense technical part of the talk, any questions, thoughts, comments, or death threats about this kind of cute toy example? No thoughts. Okay. I hasten to add, in case you think, okay, I'm going to go use this gauge theory of currencies in order to write an economics paper. This is not a good theory of economics. You should not ever try to do finance using gauge theory. So we're not attempting to really model the economy. This is just a cute toy model. This is just to get intuition for the physics. So don't offer to collaborate with Greg's dad to write a paper on this, the line bundle connection theory of finance or something. But,
wait,
okay.
So the extra money that we made from exchanging like that, does that correspond to the junk we had before, which was stopping it from?
Oh, good. Yeah, it will turn out to be related.
Okay.
It's not exactly that term, but the fact that we could make money by going in this way is really telling us that to compare prices at different points, we need to use a different derivative, something called the covariant derivative, which we'll see, and that will be exactly related to the junk that was in the first act. That's right.
Okay.
Good. All right. So if there's no other thoughts, I will do a little bit of math, but not so bad. This is just calculus and like 2D like vectors. So this is really just pictures, nothing sophisticated here. So the goal is to get some equations by starting with the intuition we had before and making it a little quantitative. So This section will push that analogy a little bit by having an infinite collection of countries. We're going to put these countries on a grid or a lattice. This is sometimes called lattice gauge theory. And again, even though this is a cute toy example, the equations I write down are the equations you will see if you open a textbook on lattice gauge theory. So this is actually useful. And our goal is going to be to get equations for three different things. We want to see quantitatively how does an exchange rate change under currency rescalings, which is basically what Tetra said at the beginning, measuring this theta 1 minus theta 2. But as it turns out, it will be convenient to introduce exponentials so that we can change between differences in quotients, basically. So we'll do that quantitatively. We'll write down a field which measures how much money you would make by exchanging currencies in a loop, just like this example where we doubled our number of Deutsche Marks. And we'll write down a derivative which compares prices in nearby countries. This is the covariant derivative I was hyping up a moment ago. And then finally, even though we're on a lattice, I'll take a continuum limit, so our equations will now be accurate for functions, not just for lattice values. And again, in case you're unhappy because you think this is all very silly or something, I just want to emphasize that we will get accurate equations for U1 gauge theory. So even though I'm being a little cavalier by talking about money, it's actually useful. Okay, so enough talk, let's actually do it. So let's go to the lattice. When I say lattice, I mean at each integer valued point in the plane, so like 3, 3, 3, 2, 4, 2, at each point in the plane with integer valued x and y coordinates, we're going to put a country. And I'm just going to talk about a vector n, which has some n1, which is the distance along the x direction, and I introduce this unit vector e1, so this is just the vector pointing to the right, and e2 is the vector which is pointing up. So I have a lattice, one country at each of these points. And to kind of formalize this exchange rate idea from the previous section, we're going to say all these countries are connected by bridges, so there's like a link, if you like, between each pair of points on the lattice that are adjacent. And on each of those bridges is a bank. So there's a bank sitting here, and when I walk from one country to another, I must exchange all of my old currency for the new currency. So I walk from one point to another, and I must change to the currency of the new country. So that's the kind of mathematical picture for the money bundle, if you like, that we had before. So to be very concrete, maybe we say Germany is sitting here and France is sitting here, so they're separated by some unit vector e1, which is pointing to the right. So this is just, kind of putting infinitely many countries in with the idea we had before. Okay, so what is the exchange rate? I'm going to abuse notation a little bit. Since I said at the beginning, I like to use this index mu for a space-time index. So usually mu is in the set of t, x, y, and z. I'm going to abuse notation a little bit because these equations will end up being correct for space-time if we let the index be mu. But for now, forget mu as a space-time index and just think of mu as either 1 or 2. So it's either the x or y directions. So this function r is going to be the exchange rate between the country at a point n. So it takes in n as an argument, and it spits out the exchange rate at n for currency at n plus the unit vector. So for instance, r sub 1 at n is the number of francs. So it's the number of francs we get per Deutsche Mark because 1 is the unit vector pointing to the right. So similarly, R2 at this point n would tell me how many units of the currency at this point up here I get per unit of currency in Germany. Right? So the two indices just tell me which direction I'm walking in, and the number that is output tells you the number of units of currency at that end point you get in terms of currency at the start point. So that's our exchange rate function, this r. Okay. Now, it ends up being useful, as I was saying before, because we're going to have a lot of products and quotients, and we know that logarithms are nice because they let us turn, say, products into sums. So I'm going to define another function a mu, which is just the logarithm of the exchange rate. So this function I told you about before, r sub mu, just take its log, and then that's going to be our a sub mu. Or written the other way, you could say r sub mu is the exponential of a sub mu. And you could say, okay, why would you do this? This seems unmotivated. It kind of is, but it will help us compare with the electron example, because in that case, we were rotating by some function which sits in an exponential. So to compare, it will be useful to have another function which is sitting inside an exponential. That's one way to motivate it. if you know more about Lie groups and Lie algebras and manifold theory, you might think I can give a better motivation if you have that background, because if in that case you know that if you exponentiate an element of a Lie algebra, you get an element of the corresponding Lie group, right? So for instance, the circle, which is U1, the Lie algebra to U1 is just the set of tangents here. So the Lie algebra is just basically I times the reals, and if you exponentiate I times the reals, of course you get the circle. You get U1, right? So it's a general fact that if you exponentiate tangent vectors, you get finite points along a flow. So that's really why this is useful, but I won't dwell on this too much because I don't want to assume much background. Okay, so that's the log of the exchange rate. Now let's think about gauge transformations. So as I was saying before, we want to allow all currencies to rescale simultaneously. So let's say we do that using a function f. So f takes in a point n, and it tells you the factor by which the country at that location n rescales. So in the example with Italy going from the lira to the lira tilde, it would have been f of n outputs the number 10 at the point n where Italy sits, right? So it's just rescaling their money bundle by a factor of 10. And again, to compare with the other example, I'll sometimes write f of n as the exponential of some other function epsilon. So epsilon is just really the log of f. Okay, so now we want to get an equation out. So here's a question for you to think about for a moment. Again, the exchange rate r sub mu tells you how many units of the currency at the location n plus e mu you get for each unit of currency at n. And now I ask the question, if we rescale currencies everywhere by a function f of n, how does the exchange rate r sub mu change between 2 points in terms of f? So that's a little abstract. Let me make a more concrete example. So if I'm sitting here with $100 and Greg is sitting here, and I lose a bet to Greg, so I need to pay him, but I'm paying him in, say, pounds. So if the old exchange rate was 1-to-1, I would pay him 100 pounds. And now suppose we rescale the currencies only in the UK. So f of n being the UK, if n is in the UK, suppose it's 2. So now the UK has a new currency, pound tilde, and 1 pound tilde is 2 pounds. So how much do I need to pay Greg now? Well, before my $100 went to 100 pounds. Now 100 pounds is only, what did I say, 50 pound tilde. So in this case, the exchange rate is no longer 1-to-1, but it's 1-to-2, right? The exchange rate has been rescaled because the UK went from the pound to the pound tilde. That's the concrete example. Okay, now I'll let you think about it. So in the more general case where f can be arbitrary, so f of n and f of n plus e, say I, are arbitrary numbers, what is the new exchange rate as a function of the f's after such a rescaling?
It would be a ratio of the values of r at each, or no, not of r, a ratio of the values of f of n and f of n plus whatever the unit vector is, depending on which direction.
Yeah, good. So which way should it go? Which f of n or f of n plus e? Which one goes in the numerator?
Well, if it's an exchange rate that you're like multiplying your starting country by, then you would of course have the starting country in the denominator and then the ending country in the numerator.
Yeah, good. That's right. So the starting country goes in the bottom, f of n, and the ending country should go in the numerator because of this example. Like in the case where the ending country was the UK, f of n plus e mu. Good. So the exchange rate indeed is rescaled by the ratio of these kind of local rescalings at the 2 points, right? So this is almost exactly what you said in the first act about the theta 1 minus theta 2, except here it's a ratio. The reason it was a difference there is because we were talking about the logarithm, right? So I'll take the answer you just told me, which is that indeed, under such a gauge transformation, the exchange rate goes to the ratio at the ending country divided by the starting country times the old guy. And in order to make this look like the angle thing, we're just going to use the logarithms. So if I replace r with this exponential of a mu and replace f with the exponential of epsilon, this is, this r is now this exponential of a mu. I'm just replacing everything in this equation with the exponential versions. This ratio goes to the ratio of these exponentials. And the nice thing about the exponentials is that this quotient now turns into a difference. So in terms of the logs, a mu, this conversion factor, just changes by a simple difference. So this is indeed exactly like the theta 2 minus theta 1. It's just a simple difference of the epsilons at the 2 points. Now I boxed this equation because this is answering basically, at least in the discrete case, the first question we wanted to do in this section. How exchange rates change under currency rescalings. So that's done the first answer we wanted. So this is a useful equation. It will look a little more familiar at the end when I take the continuum limit, which will be quite fast. But so for now, just keep this in the back of your head. And now let's answer the second question about how much money I make. So I'll ask another question for you. So suppose I generalize this thing about making money with the Deutsche Mark. I start with 1 unit of currency here at a point n, and now I'm going to go in a loop. I first go to the right, so along the unit vector E1, and I exchange it for money at n plus E1. Then I go up, I exchange it for money at n plus E1 plus E2, which is up here. Then I come back, so I'm going to the left. This is the only tricky part of this question. I come left to the country at n plus E2, and then I come down to the country at n. So how much money do I make if I started again with 1 unit? Can I write an equation for the amount of money I end up with as a function of these various r's? And the one hint that I'll tell you is that, remember, r mu tells you the exchange rate between kind of n and n plus e mu. So it's a, for instance, for r1, it's telling you how much you get for how much money you get at the country that's 1 unit to the right. So the thing you have to think about is how to do this for n minus e mu. How do I get an exchange rate for a country 1 to the left? But okay, think about that for a moment and chime in if you have a proposal. Maybe I'll ask an easier question first. So the first step, let's not do the whole loop at once. Let's start with 1 unit here. So here I have 1. When I go 1 unit to the right and I'm sitting here, how much money do I have in the local currency when I sit here after the first step?
N times r sub I or r sub 1 of n.
Yeah, exactly. And that's by the definition of the exchange rate, n times r sub 1 of n. And then when I go up, now,
so you just continue multiplying by the various factors.
That's right. So here it's n times r1 at n times r2, or sorry, r2 at n plus e1. Now the only trick is when I go to the left. What should I do when I go to the left? Because if I had
You have to divide.
Yeah, good. You have to divide, exactly. Because here the exchange rate r1 at this point would tell me how many units of currency here I get per unit currency at the starting point. So if I divide by it, that tells me how many units of currency at this point I get in terms of the currency at this point. So dividing is exactly what I want to do. That's right. So if I start with n units, I go to n times r1, n times r1 times r2, and then I here need to divide by, well, which one do I need to divide by? Well, it had better be r1 at the point n plus e2, because I'm dividing by the exchange rate at this guy in the top left. And now you see the pattern. So I divide again by r1, r2, divide by r2, if I'm doing this right, at probably n, right? Because r2 would give me this currency in terms of this currency, so I want to divide. So if I didn't make any mistakes, I think this should be right. Start with n and then multiply by this ratio. And let's go forward and see if I did it correctly. R1 at n, R2 at n plus E1, R1 at n plus E2, R2 at n. Good, good. Okay, so we were correct. I'll define that number to be a gain factor. So for instance, the gain factor was 2 in the Deutsche Mark example. So the gain factor, say G12, where 1, 2 is because I first go along the 1 unit vector and then along the 2. That gain factor, as we just argued, is this. So it's this R1, R2 divided by R1, R2 at different points. And if we were more general and said, okay, it doesn't have to be 1, 2, it could be to any, e mu and then e nu, we're just using the Greek letters mu and nu, then the gain factor would be the same thing where I replace the 1 and 2 with a mu and a nu. Okay, so this is our gain factor. One last question for you. if we do the same game we've been playing before, where I want to write all of these in terms of the logarithms, so g is now going to be some exponential of f mu nu, and all of these r's are now going to be e to the a mu's. So you could probably see that it's just going to turn into sums and differences instead of products and quotients. Can you guess or figure out what the equation for f mu nu is going to be when I replace everything with the exponentials in this line?
Wouldn't it just be a mu plus a mu and plus all the other terms?
Oh, I think you cut out for 1 second. You said it would be a mu and then what else?
A nu, so plus a nu.
Yeah, at a mu, there'll be a sum, but at they'll be evaluated at the different points, I guess is the point. So there'll be indeed this r mu at n will give me an a mu at n. This r mu at n plus e nu, it's in the bottom, so it'll be minus, right? Minus a mu at n plus e nu. And then this guy in the top, this r nu will give me a plus a nu at n plus e mu. And then the guy in the bottom will be a minus a nu at n. Yeah. So it's just everybody in the top is a plus and everyone in the bottom is a minus, but I have to keep the argument straight. Good, indeed. So that's correct. If we start with, again, this gain factor written this way and substitute in the exponentials, just writing the same equation in terms of these exponential quantities gives us this thing. And now I just read off the exponential. F mu nu is this thing. So it's the difference of the a nu's evaluated at different points and the difference of the a mu's evaluated at different points. And if you know multivariable calculus, you'll see, okay, this is looking suspiciously similar to a partial derivative once these e mu's are getting smaller and smaller, if we take a limit. So that's exactly what I'm going to do next. So that'll be the last thing for this section, is take a limit so that this thing turns into partial derivatives, which is what we want for the continuum. So at the end of the day, we don't want a lattice of countries, we want a continuous space. So if you imagine zooming out from the lattice so that the points are getting closer and closer together, morally speaking, this should really approach kind of a function or a theory, I guess, on R2, right? Because if these points are so close together, then it really doesn't matter that they're discrete anymore. It should turn into a continuous theory on the plane. So mathematically, how do you do that? You say, well, okay, the distance between adjacent points is not 1 anymore. It's now going to be some distance a, right? So the lattice is now replaced by a lattice of points at a times integer valued ordered pairs. And a is now called the lattice spacing. So for instance, maybe here a is 1, then it goes down to like a is an eighth or something, and then, I don't know, here's very small, a is, I don't know, 1 over 128 or something like that. And eventually we take a to 0. So we should be able to do this in all of the equations we wrote down. Take a to 0 and get some sort of continuum quantity. So let me do that for you. I'll recall the first equation we wrote down. Under a gauge transformation where everyone rescales their currencies by some function f, which is e to the epsilon, a changed in the following way. It was a difference of epsilons at nearby points. So now what I want to do is say, okay, I don't want an exchange rate a anymore. Now I want the exchange rate per unit distance, right? So this tells me how much exchange rate I accrue when I go a distance along the lattice. This is the right quantity to think about. If you know differential geometry, it's basically because a has one downstairs index. So, I mean, this motivation won't be particularly convincing unless you've already heard it before. But a has a downstairs index, so it's covariant, if you like. So when you rescale coordinates, it has to pick up a factor of a, which is basically the reason. But if you don't like that reasoning, then just say, okay, well, it doesn't make sense to talk about exchange rates between adjacent points when they're very, very close together. It makes more sense to talk about an exchange rate per unit distance. So let's do that. A tilde is the exchange rate per unit distance. That simply means that a, the total exchange rate, or log exchange rate if you like, is the distance a times the exchange rate per unit distance. So this tells you the exchange across a lattice spacing, if you like. And now let's just rewrite this equation in terms of the a tildes. So I replace everywhere I see an a, I put a lowercase a times a tilde. So I just do that everywhere. So do this, replace this with a tilde, blah, blah, blah. And now I just play a little game where I factor out an a. I factor out a lowercase a, and what I'm left with is an a tilde plus something that looks suspiciously like a derivative. So once you see this thing, you should say, aha, this is perfect. Now I can take the limit as a goes to 0. if I take the limit as a goes to 0, this is precisely the definition of the partial derivative of the function epsilon in the direction e mu. And my notation for that is to write this partial with a subscript mu. So partial with a subscript mu just means the partial derivative of the function epsilon with respect to the basis vector in the mu direction, x mu. Perfect. Okay, this is kind of the starting point usually when one studies gauge theory in terms of this gauge field A. So for a continuum gauge field, this is the way that the gauge field transforms under a gauge transformation. And if you've studied calculus on manifolds, this might have a sort of cohomological flavor, because it's really saying you can shift this one form A by any exact form. A goes to A plus dA, if you like. So again, if I were Greg giving this talk, I could say some things like, flat connections, which is gauge fields A whose curvature vanishes. Flat connections are just characteristic representatives of cohomology classes, because they're all gauge equivalent if you shift them by exact forms, but since they're flat, they're also closed forms, right? So it's very cohomological in flavor. Anyway, I'm not going to dwell on that. Let's do the other continuum stuff. So what about the money you'd make in a closed loop? Well, we wrote that equation before. We wrote this gain factor g in terms of an exponential of f. Going in a closed loop was just this weird combination of differences of a evaluated at different points. And now I do the same thing. I replace a, the log exchange rate, with a log exchange rate per unit distance, a tilde. I replace my f with an f per unit area, which is the right quantity to think of because f is going in a closed loop, so you might think it should depend on the area, or if you know differential geometry, it has to be a squared because this has two downstairs indices, which probably sounds very mysterious. But anyway, in either case, if we rewrite this equation in terms of tilde quantities and factor out an a precisely as I did before, I get this equation, a squared times this quantity, which again looks suspiciously like a combination of partial derivatives. So now we're gold. You just take the limit as a goes to 0 again, and this is now the partial derivative of a sub nu, right? Because this term is a difference of a sub nu's evaluated at nearby points in the mu direction. So that's the partial mu derivative of a tilde nu. And this term over here is a difference of a mu's evaluated nearby in the nu direction. So this is a nu derivative of a tilde mu. So this is the definition of the field strength tensor in electromagnetism, but for us, it's just measuring the money you would make in a closed loop. And again, if I were Greg, I would say, okay, it's trivial, it had to be this, because the only way to make a two form out of a one form using the derivative is to take the exterior derivative, so it has to be f as dA. But that sentence doesn't really give you much intuition for what it's doing. The reason why the exterior derivative is a good thing to do is because of this going in a loop argument, right? This is the intuition for it.
Okay, so that equation tells you how much the logarithm of the gain factor changes under a gauge transformation around like a closed loop, right?
Oh no, so there's no gauge transformation in the game. So we're not doing a gauge transform, we're just fixing exchange rates a tilde. So a tilde is fixed once and for all, we're not changing them. Okay. In that given background, this measures how much money you would make given those exchange rates. Right. So for instance, like F12 might have been like log 2, for instance. If F12 is log 2, you can double your money by going in a loop. Indeed, you pointed out that the gauge transformation comment, this thing had better be gauge invariant, right? Because we argued before that if anyone rescales their currency, how much money I make would not change. So this F had better not change, right?
Okay.
Very good. Yeah.
Just another question. Is there meant to be a lowercase a next to a tilde mu when you factored out the a squared? Because
Oh, good. Yeah, sorry, this is wrong. Yeah, I copy pasted the equation and went through and changed the a's, and I lost one. Very good. Good catch. I will correct that before posting the slides. Very nice. Other questions? This is a nice big result. Maybe one more Greg type comment. An easy way to see that this is gauge invariant, f tilde is dA, where d is the exterior derivative. This had better be gauge invariant because the gauge transformation looks like a tilde goes to a tilde plus d epsilon, where epsilon is this gauge parameter, but d squared is 0. So taking d of a, if I change a tilde to a tilde plus d epsilon, then this is the same as dA tilde, because d squared is 0. So this is a quick way to see that f had better be gauge invariant, because it's taking two exterior derivatives, if you like.
And the reason why d squared is 0 is because we're just scaling, like just by a scalar value, or is there something?
Oh, the reason why d squared is 0? Well, d squared is 0 because the exterior derivative is basically antisymmetric, right? So the reason why d squares to 0 is basically because if you imagine taking take a function f, and then I hit it with d, then this is like some vector. It turns a scalar function into a one form, so it's like a vector dx of f, dy of f. But then when I take d again, taking d again is now taking some antisymmetric combination of derivatives. So like one entry of hitting it with d again would be dy of the first component, so dy dx of f, minus dx of the second component, minus dx dy of f. So one component of the d squared acting on f would be this guy, but this thing vanishes because the partial derivatives commute. So if you define d in this way, yeah, it looks weird if you haven't seen the definition of d on an arbitrary p form, but the definition of d has this antisymmetric property, which means it vanishes if you do it twice, basically.
Okay.
Good. All right, so we're almost done. I need one more thing from this section, which is how to compare prices. So this is finally going to loop back to the electron and fix the problem that we had. So for the last trick, and then I promise I'll stop because I'm almost over time, how do we compare prices at nearby points? So say I'm measuring, I'm speculating on the price of copper, and I want to see if I can make money by trading copper. How do we compare the price of copper at two nearby points? Well, I can't just subtract. I can't just evaluate my price function p at n plus e1 and subtract p at n, because I'm comparing apples and oranges, right? I'm comparing the price of copper in different currencies like francs and Deutsche Marks, for instance. So what I really need to do is use this, I'm going to call it capital delta, but it's not really a naive difference. It's a more sophisticated difference where you measure the price of copper at the point x plus dx in the currency at x and subtract the price at x. This is a better delta to do because you're differencing two quantities measured in the same currency, the currency at x. So what does this delta look like where we use this exchange rate? Again, 1 over r is the exchange rate you would use to go back to the left. So mathematically, what does this look like? Well, it's a little dense, but if we again write the exchange rate with this exponential, r mu is e to the a mu, and use this a tilde, which is log exchange rate per unit distance, then the total exchange rate between n and n plus a e mu is this, lowercase a times a tilde. That's the total exchange rate. So what I should do to compare the prices is I take the price at in the wrong currency. This is the price in the wrong currency. I divide by the exchange rate to turn it into the right currency, and then I subtract the price I'm comparing it with. So I'm just going to Taylor expand this basically. So first I replace this r mu with this exponential, where the total exchange rate again is a times a tilde, and there's a minus sign because it was in the denominator. So this is the price in the wrong currency times the factor which corrects it to the right currency. And now all I do is Taylor expand this exponential e to the minus a. E to the x is roughly 1 plus x for small x. And I'm going to eventually take a limit as little a goes to 0 anyway. So I might as well just keep the first term in a Taylor expansion. If I do that, here's the old term, the factor that came along for the ride. Here's the Taylor expanded piece that just came from the exponential. And this also came along from the ride. It was just subtracted. And then plus higher order terms. So again, only keeping terms to first order. If I factor out an a in the way that I did before, now things are looking good because I have these two terms which came from when the p hit the 1 and subtracted the p. That thing looks like a derivative. I have one extra term which is from when the p hits this term. So that's the a tilde times p. And now I'll take the limit as a goes to 0 and I will define this to be a new object. This is the covariant derivative. So this new object is capital D sub mu, which is defined as the ordinary partial derivative minus this additional term, this a tilde times p. This is the new derivative, which I argue is the correct derivative to use to compare prices when the currencies can change. Good. questions on this, since this is a bit of a dense slide, but it's also important. If there's no, oh, sorry, what is it?
When I'm getting this like extra stuff like this minus a tilde mu and so forth, I'm still thinking of the junk that we had at the start. Like,
Yeah,
is that anything to do with the junk that we had at the start?
this is exactly the thing which fixes the junk. So I'll fast forward a little bit. So that junk that we get with the extra a mu, if you use this derivative, it exactly cancels the junk. So you're right. You're exactly right to think of the junk. If we use this derivative instead of the naive derivative, then the junk goes away, and it is asymmetry. So indeed, you're exactly right to recognize the junk. The covariant derivative is precisely the object which would destroy the junk that was generated by the naive partial derivative. That's right. Good. Maybe just to keep you on your toes a little bit, one question before I wrap up. I did a little algebraic trick here. There was a term which was p evaluated at n plus a e mu times a tilde at n. In the next line, I wrote it like this: a tilde at n times p at n. But p at n is not the same as p at n plus a e mu. These terms are not equal. So why was I allowed to do this? Did I make a mistake?
I mean, it's something to do with the fact that the price, or not. Never mind. I've forgotten what. What is What do we mean by p of what is this function p again?
P is measuring the price of, say, copper at each lattice point n.
Right.
It's a price
Yeah.
function. Yeah.
So if we, I guess it must do the scaling for you, sort of like when you go from a times a tilde mu of n, then the scaling, like, I guess it must cancel. I don't really understand why that would be.
Yeah, it doesn't actually cancel. The trick is the following. I fooled you a little bit by only keeping terms to the first order in A, because
Okay.
right, what I could do is say P at n plus a times e mu. Well, this is really, if I use the tangent line approximation, this is really P at n plus a times the derivative of p. This is just saying that if I want to evaluate a function at f at x plus dx, I might as well say it's f at x plus the derivative times dx, right? Plus dot dot dot. So I sneakily under the hood used a first order Taylor series for this p, but this term is multiplying a, and if I multiply that by a term which already has an a in it, then the resulting term is order a squared. And I don't care about terms of order a squared because I'm going to take a to 0. So I'm allowed to replace it as long as I stipulate that I'm only keeping terms of order a. That's the reason. It's a little sneaky, but just to be pedantic, I wanted to ask that and keep people on their toes. But okay, good. All right, so we're basically done with this act. So I'll just wrap up in a couple minutes really quick and preview some other things we could discuss. But just to review what we did, in this act, we use the lattice. We put countries on a lattice with a continuum of money spaces and a local exchange rate R mu, and we derived 3 facts. If you do a gauge transformation, if you locally rescale prices in this way, then the exchange rate changes by a derivative like this. That's the first fact. The second fact is that if you trade money in a closed loop, you can make a profit which is measured by really the exponential of this function f, which looks like an anti-symmetric combination of derivatives of a. And the right way to compare prices is with this fancy capital D derivative, not the ordinary derivative. And these are kind of the fundamental equations of U1 gauge theory. This is all we really need. Okay, so that was a little dense. That's the end of the actual talk, but I have an epilogue just to wrap things up a little bit, which should only take a couple minutes. But before the epilogue, any other thoughts or questions? Okay, no questions. All right, so I'll try to wrap up so I'm not keeping you too long. But all right, just to connect so that I convince you that all of this money faffing around was actually useful. Back to the electron. So the whole story started because we wanted to upgrade this symmetry of the electron field to a local phase rotation at every point. So now we see how to do that, right? Before I said what we roughly want to do is attach a local copy of the circle at each point. And if I didn't say it before, when I say U1, I really just mean, the set of all e to the I thetas, right? The circle thought of as a group of rotations, if you like. That's what U1 is. So all we really do is attach a little U1 circle to each point at spacetime that is measuring how much the electron phase has been locally rotated. And then I said we would need a conversion factor to compare the angles between points. But now we know exactly what that conversion factor is, right? Because allowing such local phase rotations is precisely like allowing local currency rescalings. So now we know what to do. What we do is introduce a new field, A sub mu, which is the exchange rate on the circle, basically. It's an exchange rate for electron phases at nearby points. And this should fix all of our problems as long as we use the covariant derivative now instead of the ordinary derivative. So the only difference is that now, before it was R mu was e to the A mu. The only difference is that now, since there's an I in the electron phase rotation, I also need an I in the covariant derivative. That's the only difference. So if I define this covariant derivative, capital D mu is del mu, or partial mu, minus I A mu, then as Greg pointed out, or kind of predicted, this exactly fixes the junk. So the problem we had, just to remind you, way back on slide 16, was that you get this junk where the derivative can accidentally hit the theta and give you this term that breaks the symmetry, and that was bad. But now, if I go all the way back to here, if I say, okay, my good term is not just psi bar d psi, it's psi bar capital D psi, then this extra minus I A mu term, when that minus I A mu hits the psi bar and the psi, then that generates an additional term, which is this minus I A mu sorry, I'm saying this wrong. There's two steps. We replace this with a partial derivative. Then we recall that when we do a gauge transformation, both the electron phase changes, but also A changes by a derivative. That's the missing fact. If I do a gauge transformation, I need to both replace the electron phase by e to the I theta of x times the electron, and I need to change A. The fact that A changes under a gauge transformation is just the fact that if I rescale currencies, the exchange rate has to change. So if I recall that fact, this fixes our problem because now under a gauge transformation, two things happen. One, the electron phase changes, and two, A shifts by a derivative. And the extra shifting by a derivative exactly cancels the junk. So that fixes it. Now this thing has the symmetry we wanted. Okay, so to conclude, the first vignette I told you was about this Aronoff-Bohm effect. So this is exactly the same as making money by going in a closed loop. With exchange rates, you could go in a closed loop and make money. In electromagnetism, you can move an electron in a closed loop and end up with a different phase. So in this Aronoff-Bohm effect that we all started the whole talk with, I shoot electrons around a solenoid, and their phase changes when they hit the screen. Now we know that that's because there's some connection with curvature. There's like exchange rates, and in the same way as going around in a circle makes money sometimes, the electron going around in a circle in the presence of a magnetic field allows the phase to change. And that's why this thing has an interference effect on the screen, which changes when we crank up the magnetic field, crank up the curvature. So this is why the Aronoff-Bohm effect happens. There's curvature, and the electron phase changes for the same way that we could make money in the currency example. Okay, so just to conclude, if you get one thing out of this talk, it's that electromagnetism is a U1 gauge theory. So when you study gauge theory, you say that this field A sub mu is a connection on a U1 bundle. Its curvature measures electric and magnetic fields. And I haven't done any quantum mechanics, but if you quantize this theory, A mu gives you, the quanta of A mu are photons. So if you hear the word photon, it's just a little fluctuation in A mu in quantum mechanics. Here we use the group U1 because local gauge transformations are on the circle, but you could replace this with other local gauge transformations. So for instance, if you study the strong nuclear force, you use a different group called SU3, and the gauge field there is a gluon. So this whole thing is kind of the entry point into thinking about a subject called principal G bundles. When I talk about principal, the word principal just means it's a fiber bundle whose fibers are a Lie group, that G is a Lie group. Okay, so I'm going to skip this part. I included this so that I could just make a connection with Greg's talk, because he basically started with this definition and I end with it, right? I wanted to slowly build up intuition to motivate what a fiber bundle is. A fiber bundle is just a space with another space attached at every point. So here's the formal definition which Greg started with. If I had more time, I would just go through and explain that this definition precisely matches our intuition, that if you have, like, for instance, a circle with a little strip attached at every point, then this has some properties like you can take inverse images of a point and get a little strip. It's supposed to look like a Cartesian product locally, blah, blah, blah. This is how I would motivate bundle theory, by talking about it as having a space attached with certain properties. But I'm not going to go through the formal definition and explain how all the pieces fit together for time reasons. Just one quick aside on the definition, because I went back and looked at the slides from, I think it was Tetra's talk on the Rubik's Cube, which talked about group extensions. I just wanted to briefly mention one fun little analogy, that if you write the definition of a fiber bundle like this, so it looks like a short exact sequence, it looks very similar to a group extension of Q by N. So you can really think of an extension of Q by N as an N bundle over Q, right? You should really think of group extensions as a fiber bundle where, the inverse image of a point on the base, which is like Q, gives you some fiber, which is N, right? And the overall group is somehow like the bundle. And this analogy is very nice because, these extensions are classified by group cohomology. They don't have to split in the same way as fiber bundles don't have to be trivial. So there's lots of cute analogies there. I'm going to skip that. And just to conclude, I'm going to say, when I started writing this talk, I intended to do everything I just said, and also this, which obviously did not work out because I'm already over time. So I'm just going to flash a few other things you could do. You could replace U1 with a group where the rotations don't commute. You could do quantum mechanics, which I haven't done. You could use bundle technology to talk about topologically non-trivial configurations like a Mobius strip, which is like a magnetic monopole. And you could also talk about other gauge theories besides Yang-Mills and Chern-Simons. It turns out it's very hard to write down other gauge theories that satisfy certain sanity checks. The only non-abelian gauge theory I know of besides Yang-Mills and Chern-Simons, which passes basic sanity checks that I'm aware of, is this paper that I wrote last year about a non-abelian analog of this DBI theory. It uses TT bar. This is the only one I know of besides the standard examples that you can actually write down and study in detail. But okay, I'm way over time, so I'll stop. Thank you, and I am happy to discuss and take questions.
That was great.
Thanks. I guess I'll stop.